Right, welcome back again. This video is a continuation of the percentile, quartiles, and also interquartiles materials that we just discussed earlier. Now let's move on to what I promised for the second section is the coefficient of variation and z-scores, and I think we have enough time. We can also talk a little bit about shape, that is skewness and kurtosis. Now, the coefficient of variation is very important when you have two different data sets with unequal size. I think we talked about this when we were discussing the frequency tables, and we talk about the relative frequency. We use percentage to compare and describe two different data with unequal sizes among them. So if you look back at the restaurant, the menu, the cost for per meal for city restaurant and suburban restaurants, the city restaurants have more restaurants, and the suburban restaurants have less restaurants. And so when I only look at the frequency, just using the value, for instance, the average is 50 and the average for the suburban is 70, then it doesn't really describe the idea of equal comparison, because again it's unequal sizes, so you can't really compare them equally without converting the scores for each restaurant to a percentage. So therefore, using relative frequency is quite nice because it does put the two different data sets in more or less equal position. And also the coefficient of variation, it gives a relative measure of the variation among the two different data sets. Okay, so the coefficient of variations is usually denoted by symbol CV. CV equals to the standard deviation divided by the mean, the mean of the data times 100, because we want to convert it into percentage. Now let's move on to Z-score. So what is Z-score? Z-score is this standardized score because we want to standardize the scores in our data set in order to minimize extreme value or outlier. The z-score, if you look at here in the formula, it equals to the x minus x bar. X is the each given score minus x bar, which is the mean, divided by standard deviation. Standard deviation, you obviously still remember the formula is sigma times x minus x bar squared divided by n minus 1. So it's pretty close to the calculation of variance, but in standard deviation you have to divide it by n minus 1. Okay, values located far away from the mean will have either very small negative z-scores. So again, I keep bringing up this drawing because I would like to start introducing you to what we call normal distribution, because in statistics we really would hope so much that whenever we collect data, we are hoping that our data will look like this. Let's say this is the mean or the mean population, mu, and then the scores would scatter around the mean. Hopefully not so much over here or over there. Why? Because then we will have skewed data. That is something that we will talk about after the z-score. But anyway, we if we do end up with, let's say, data that is not quietly distributed, or let's say like this, that is like this, for instance, you see a lot of scores are here, so there are only few here. So it's what we call left skewed, because left tail here. So what we do is uh, we use the ZScore. We standardize the scores in order to somehow normalize the scores and make our data set look more normally distributed. Okay, again, Z-score, the function is to minimize the effect of extreme value or outlier that is given in our data set. Okay, this is for example. Here is the normal data, the normal scores that we get. If you remember the serial data, these are actually coming from the serial data, and you get the mean here, x bar, 80 plus 100 plus 100 plus 110 plus 130 plus 190 plus 200 divided by 1, 2, 3, 4, 5, 6, 7 scores. So equals to 130, and before you are able to compute the z-scores, you need to compute the standard deviation first. So what you need to do is just simply sigma x minus x bar, just like we did in the previous video, using a table, and then divide it and minus 1. And there you go, you got standard deviation, which is 46.90, and then that's when you can start calculating the z-scores. Z is equals to x minus x bar divided by s. So if you calculate it yourself, we can just have a computer, the calculator in your hand. So the first score, that is 80 minus 130, that is negative 50. Negative 50 divided by 46.90. So what do you have? You end up with a negative 1.066 something, and then is rounded up to negative 1.07. The same thing for the second score. The second score is 100 minus x bar, that is 130. You end up with negative 30 divided by the standard deviation, so you will have negative 0.64. The real calculation is actually negative 0.6396, but you again round it up to the closest value, that is negative 0.64. Okay, so that are coefficient of variation and z-scores. You know when to use them. If we do a little review, starting from the percentiles, whenever people ask you now, you got so many statistical calculations, when to use them. Again, you look at the data, what do you need, what do you want to perform. For instance, if you are just to locate which scores fall below the 90th or the 50th or the 75th, then you look at the percentiles. What is it good for? Well, it's good to identify which score is actually the highest, or which score is actually considered high. That is 75th percentile obviously is quite high, and which score is low. We can always have a range of, let's say, a score of on a test. It can start from 0 to 100, right? But we cannot guarantee that the highest score for one class would be 100, even though the range starts from 0, from the smallest to the highest, that is 100. So maybe the highest is only 75, So we know that 100th percentile would be, or 90th percentile would be 75, but then we don't know. Okay, then which scores fall below the 90th or the 70th percentile, let's say, because you want to kind of figure out what is going on in your class. For instance, do we score good on the test? Do we not score good on the test? So that's percentiles, and also it comes with quartiles and interquartiles. If you are interested in, let's say, talking more about the position of the data set. And then you have coefficient of variation. For instance, you are comparing two data sets. You are comparing two test results from two classes with different sample sizes. Your class has, let's say, 40 students, and the other class only has 30 students. So when you say 50, does it also resonate with the other class, 50 as the average? Does it also resonate with 50 in the other class? Then if to be sure, then you need coefficient of variation to compare the two data sets. And finally, the Z-scores. The Z-scores are really useful when you have extreme scores or outliers. And also, if you want to have some kind of standardized scores, then yeah. What I mean by standardized score is, if you look at this here, see here the Z-score is 0, so it is the standard scores. Mean becomes the standard scores. Mean becomes the reference point. Mean becomes the starting point of a given data set if you're using Z-scores. Instead of, let's say, in this raw data, 0 is the, let's say, the starting point, right? Or 130, for instance. No, I'm sorry, not 0. But 130 is the starting point, right? The average. But now it becomes 0 in the Z-scores. You see here, the once we convert the mean to a Z-score, then the difference between each scores are becoming decreased, are getting smaller. Then by using a Z-score, then you can look at the difference in a more simpler way, but you have also keep it in mind that when you have 0 as the Z-score, that is 130. So when you say that 1.49, that means almost, let's say, 1.50. So when you say the highest serial, the difference is only 1.50, but you have to keep in mind that 1.50 here is actually almost double than the 130. So that's one thing to keep in mind. And now let's move on to skewness and kurtosis. So when we talk about skewness and kurtosis, these are actually the two shape-related statistics. The skewness statistic measures the extent to which a set of data is not symmetric, and the kurtosis measures the relative concentration of values in the center of the distribution. Symmetric distribution. So symmetric is, symmetric distribution is this. There you go. Yeah. So it has equal parts of each angle right side. Then the skewness value of is 0. So, but if it's right skewed, then it has positive skewness. So I will just show you the table. There you go. It's right skewed. So here the tail is on the right, so it's right skewed. It's positive, but if left skewed, the tail is on the left, then it has negative skewness. So in most cases, you can actually conclude that mean less than the median, we would end up with left skewed distribution. And when the mean is equal to the median, we have no skewness at all. That means zero or symmetric distribution. And when the mean is equal or greater than the median, then we have positive or right skewed. The tail is on the right. So that is it about skewness and kurtosis. Uh, you don't need to worry about when to use them and what does it really indicate in more detail. We will talk about it. We will get back to it again when we talk about the inferential statistics, which is after the midterm exam. Okay, thank you.